This lesson is going to be on related rates, and related rates will be one of the last major applications of derivatives. And notice here I have a lot of illustrations going on with derivatives and how you can apply them in your different types of application problems. Now before we get started in a lot of the problems, we do need to look at how to find the derivative with respect to time to a lot of general geometric formulas. For instance, for the first one, if we have area equals pi r squared, that's the area formula for a circle. And what we're going to do is take the derivative with respect to time. So it's going to be very similar to when we did implicit, the derivative with respect to the derivative of y with respect to x. Here we're going to do the derivative with respect to time. So we would say the derivative of a is 1, and then we would say dA over dt. Or you can write just dA over dt equals, and remember pi is just a number, so it's going to be 2 pi r to the first dr over dt. And what we really found here, this is the rate of change of the area, and then this is still the radius, so that is still what we know. And then dr dt, that's going to be the rate of change of the radius. So we still have a lot of similar things going on here, but we have some new stuff as well. Another common formula that we would have to take the derivative of, let's talk about the Pythagorean Theorem. But we're going to have a squared plus b squared equals, and I'm going to call it r squared because that's most of the time how you would see it. So if I do the derivative of this, we would have the derivative with respect to time, we would have 2a dA over dt plus 2b, and then we would have dB over dt equals, and the same over here, 2r dr over dt. And you can simplify, since each term has a 2 in it, you could divide that 2 out of each part. And another common formula that we would look at that we can go ahead and do the derivative of is going to be, let's do the volume of a cylinder, because that's a common one that comes up. Volume equals pi r squared h, and that is one that tends to come up. And if we do the volume, or do the derivative here, notice that we would treat this as one whole term, because again pi is just a number here, it's really just the coefficient. So when we go through and do our derivative, the derivative of v is 1, and then we would have dv over dt equals, and we would have to use the product rule here. And so with the product rule, we would do first, so I have pi r squared, there's first, times the derivative of the second. Well, the derivative of h is 1, and we would write dh over dt plus second times the derivative of the first, and the derivative of the first would be 2 pi r dr over dt. And so all of this would be a derivative that we would need to work with. Now, a lot of times, to keep from having to do this product rule, we could find some kind of relationship with R and H and change one of the variables into the other, so we don't have so much we would have to deal with. Okay, for our first problem, we have water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? We have a lot of information in this problem. So the first thing I would do would be, well, what is it even asking for? So here, how fast is the area of the pool increasing? So notice it's not what is the area, but how fast is the area increasing. So really what we're looking for would be a dA over dt. That's the first thing we're looking for. We have no clue. Well, notice if we're talking about area, we have a circular pool. So I would think that we might need the area of a circle. And the area of a circle is pi r squared. And automatically, I would go ahead and find the derivative of that formula. And most of the time, that will be your next step. After you identify which formula you need, you should be able to find the derivative of it. And the derivative of A is 1. So we would have 1 dA dt equals 2 pi r dr dt. So here's this dA here that we're looking for is sitting right there. So that's good news. We now have a formula to help us find what we're looking for. So I would go back up to the problem, and let's see what else we can find that we can use. Notice that it tells us the radius of the pool increases at a rate of 4 centimeters per minute. So the radius of the pool increases, not the radius is equal to, but it's the radius increasing at a rate. So I would say that that's going to be a dr over dt. It's the rate that the radius is changing. So dr over dt, that's going to be 4, and it said centimeters per minute. Okay, so that's dr over dt can be plugged in right here. So I'm looking for dA over dt. I have a dr over dt. Now let's look and see if I had a radius, then I could just plug in. And notice that in the very last sentence, it tells us how fast is the area of the pool increasing when the radius is 5 centimeters. So I know the radius is 5 centimeters. So that R is going to be what I need to plug in right there. So it looks like we might have everything that we need in order to solve this problem. So let's go ahead and plug in. I don't know what dA over dt is. That's what we're looking for. Equals 2 pi, and always leave pi in your answer, times 5 centimeters times, and the rate of change of my radius, 4 centimeters per minute. And so the rest of this, all we need to do is multiply this out. So dA over dt is going to be 40 pi centimeters squared per minute. And I would check my units to make sure this makes sense, since that is squared units and we're talking about area. That should work. Okay, so again, let's look at this one. Oil spilling from a ruptured tanker spreads in a circle. So I would stop there and see that it says in a circle. So I would say, well, I know the area of a circle is pi r squared, and then I know the derivative of that area with respect to time is going to be 2 pi r and then dr over dt. And so I would finish reading the problem now that I saw that that's going to be a circle. The area of the spill increases at a rate up. So I would stop here. We have a rate, and it's the area. So that tells me that I know dA over dt is going to be 9 pi meters squared per minute. So I have that part of the information. How fast is the radius of the spill increasing? So how fast is the radius increasing? That's a rate. So that's what I'm looking for, dr dt. That's what I'm looking for when the actual radius is 10 meters. And then they tell us, so r is 10 meters. So let's go look at our formula, see if we have everything we need. We're looking for dr dt. That's what we're looking for. We have our radius, and we have our rate of change of the area. So now let's go plug in. So when we plug in, dA over dt, so I have 9 pi meters squared per minute equals 2 pi times our radius, 10 meters, and then times our unknown, the rate of change of the radius with respect to time. And so now this is just a matter of solving our equation. I'm going to divide everything over. So it looks like I would have to divide 2 pi times 10 meters from both sides. So 2 pi times 10 meters. And notice I'm not multiplying all of this out unless I just have to. And so these will cancel, this will cancel, thank goodness. And it looks like over here the pi's should cancel. So it looks like my final answer, or my rate of change, dr over dt, rate of change of my radius, is going to be 9 over 20. And then let's figure out our units. It's going to be, let's see, one of these meters is going to cancel. So 9 over 20 meters per minute. Okay, the next problem, let's see, a conical paper cup. So I would stop there. And we need the, let's see, the cup's being filled with water. So we need the volume of a cone. And most of the time you should be given this formula. They're not going to expect you to remember that. The volume of a cone is 1/3 pi r squared h. And again, that's a formula that you should be given. Now, on this is one of those exceptions to going ahead and just going through and finding the derivative of everything, because this one is going to require you to do the product rule. And we really want to stay away from that if we can. So as we read on in the problem, we're going to look for a relationship between the radius and the height. And so hopefully we can replace one with the other. So it looks like we're already given something about the height here. It tells us the paper cup is 10 centimeters tall. So I know the height is 10 centimeters. And I also am told that the radius is 10 centimeters. Well, that's kind of handy. So if we start looking at a relationship between the height and the radius, well, they're both 10 here. So it's pretty safe to say that, let's see, we could even set up a ratio and say, well, h over r is equal to 10 over 10. So notice this is a 1-to-1 ratio, or the height is equal to the radius. Now, a lot of times we would see the height's equal to 2/3 of the radius, or the height is half of the radius. Something is always happening with the height and the radius with these types of problems. So here we got pretty lucky that the height and the radius are the same. Now, we really don't know which variable over here that we're going to interchange. So let's go see what we're looking for, and then that should help us. So let's see. The cup is being filled with water so that the water level rises at a rate of. So the water level rises. Well, if the water level is rising, then that's going to be the rate of the height. So that's telling me that I have dH dt. The height is 2 centimeters per second. So that helps. Okay. At what rate, oh, here it comes, is water being poured into the cup? Oh, at what rate is the water being poured into the cup? That's going to be volume. So at what rate is the water being poured in the cup? So that's going to tell me that I need the rate of change of the volume. So at what rate is the water being poured into the cup when the water level is 8 centimeters? So they went ahead, we don't know this, but they gave us another height value. The height value, 8 centimeters. So now it looks like it's pretty clear that we need to replace R with H over here because we're looking for volume, and I'm given DH. It looks like all of my information is in terms of height. So over here, I would just simply rewrite my volume formula. I'm not doing the derivative yet. And since R to H has this relationship, I'm going to plug in up here. Everywhere I see an R, I'm going to plug in an H. So that means I'm going to have H squared times H. So this volume formula for this particular problem is going to work out to be 1/3 pi H cubed. Now I would go ahead and do the derivative here. And so when I do the derivative, I have dV over dt equals, now remember 1/3 pi, that's just a coefficient. I'm going to multiply my 3 down. So I get 3 times 1/3. Well, those cancel. And then I have pi r squared, pi h squared, sorry, got another neck on this one, dH dt. And now we're ready to plug in and find our answer. So we have dV dt equals pi times our height squared. So our height squared looks like it's going to be 8 centimeters squared times the rate of change of the height, which they gave us is 2 centimeters per second. And so the rate of change of the volume, 64 times 2, 128, maybe that's right, 128 centimeters cubed, isn't it? Because we have centimeters squared, then here's another centimeter, so centimeter cubed per second. And since we are talking about a rate of change of volume, we do need that to be cubic, so pretty confident that that is probably correct. Okay, so for this one, it looks like we're working on, let's see, a spherical balloon. So, of course, we all know that volume formula just off the top of our heads, I'm sure. Let's see, that volume formula, it's a sphere, so 4/3 pi r cubed. Okay, so a spherical balloon is inflated so that its radius increases. Oops, so the radius is increasing, so that's dr over dt at a rate of 2 over r, well, that's weird. 2 over r centimeters per second. How fast is the volume of the balloon increasing? So dv over dt. How fast is the volume of the balloon increasing when the radius is 4 centimeters? Well, okay, so let's go back over and let's look at our formula, and let's go ahead and do the derivative of it. So we have dv over dt, and we could have done this at the beginning. I just went ahead and started reading the problem, but notice we only have one variable in our formula, so it's pretty safe to go ahead and do the derivative here as soon as you identify which formula you need. Here again, 4/3 pi, that's just a coefficient, so I'm going to bring that 3 down. And when I do, those 3's will cancel, so I have 4 pi r squared times the rate of change of r with respect to time, so dr dt. And so when we start plugging in, notice we need dv dt. That's our I don't know, I got to go find it, equals 4 pi, and let's see, r, well, let's see, r squared, r is 4, so I'm going to go ahead and plug in 4 here, 4 centimeters squared, times the rate of change of r with respect to time. So that looks like I need to plug in that 4 there, so I'm going to have 1/2, 2 over 4, 1/2 centimeters per second. And so we have everything we need. We just need to finish the problem. And so let's see, I would go ahead and do 1/2 of 4 and get 2 pi. And let's see, 4 squared 16, so 32 pi centimeters squared, nope, cubed, because we've got a squared here and we've got 1 here, so that's a total of 3 centimeters cubed per second. And notice our units do check out with our volume. Alright, so a 7-foot tall person is walking away from a 20-foot tall lamppost at a rate of 5 feet per second. Oh my gracious. Alright, so we have a lamppost. Of course, whatever. That's pitiful, I know. And so I've got a lamppost, and it is 20 foot tall. And a 7-foot tall person is walking away from it. So I have this person, and they are 7 foot tall, and they are walking away from the lamp. All right. And let's see, assume that blah, 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 right triangles. At what rate is the length of the person's shadow changing? So his shadow would be here. So I need to know, how is that shadow changing when the person is 16 feet from the lamppost? Interesting. Alright, so it says we can model this with triangles, and so let's go ahead and dot this in and make it a triangle. And really, I would redraw this, not just because I did a terrible job of drawing, but I would try to make it look like similar triangles, because it looks like I've got a triangle in a triangle. So I have this 7 foot tall person. I have this 20 foot. Now I need to know, how is this changing? What is the rate that is changing when this happens? So I need some kind of formula. Now it's tempting, because it said right triangle, to use your a squared plus b squared equals c squared, but I don't think that's going to be much help here. I really don't know these two lengths. I know at a particular time we would have 16, but I don't know that right off. Right now, I need some kind of formula. So I'm going to set up something that looks like this. And I would use our proportions. I know 7, we've got 2 triangles. Let me go ahead and highlight the 2 triangles we have. We have this triangle inside here with sides that we know of 7 and y. But then we also have this big triangle out here. And that one is made up of sides 20 and x plus y. It would be all of that. So if I wrote out some kind of proportion, we would really have 7 over y would be equal to 20 over x plus y. So knowing that, let's see, and that makes sense because 7 is to that side length y, as 20 is to that entire big side. So yeah, and again, we're breaking this apart because I don't need this whole side, so to speak. I want to know the rate of change of this shadow. So I'm having to break this side into 2 different parts. And that's where the x and y came from. Now keep in mind the shadow, that's what I really labeled y to be. So let's see if we can't solve this. We've got 7x. Well, I'm going to cross multiply. And I'm going to have to distribute. So I have 7x plus 7y equals 20y. So 7x equals 13y. And now I've got something with x's and y's. And I really need to go ahead and find a derivative now. So the derivative of 7x with respect to time. Let's see, that's just the coefficient, so it's going to be 7 dx over dt equals 13 dy over dt. Now we've got some rates of change going on here. So the question is, well, what are we trying to find here? I needed to find the rate of change of the length of the person's shadow. So really, if I let y be the shadow part, I'm looking for dy dt. Okay, so I know I'm looking for this portion here. Well, it would be great if I knew what dx dt was. And we do. If we go back up to the first sentence, it tells us that that person is walking away from the lamppost at a rate of 5 feet per second. That's this portion here, which is what I let x be. So technically, I know what dx over dt is. It is 5. So if we plug that in, I have 7 times 5 equals 13 dy dt. And if I divide both sides by 13, and I'm going to come way over to this other side, that tells me I have 35 over 13, and that's going to be equal to our dy dt. And we do need some kind of unit here. So let's go back up to the problem and see. The unit would be feet per second. So let's go ahead, and we don't need any bald answers there. So 35 over 13 feet per second equals our dy dt.